Alright, so today what we're going to look at is the inverse function, okay? Now, here is a very basic type of problem having to do with inverses. And someone tell me, how would we find f inverse in these cases here?
You switch over the y and the x and solve the y. It's actually resolve x.
Yeah, at some point you got to switch the y and the x, alright? Now, it doesn't matter if you do it at the beginning or at the end, as long as you switch them at some point, okay? So we could actually solve this whole thing for x, alright? So I could subtract the 1. So f of x minus the 1 is 2x. And then I could divide by 2. And I'd get f of x minus 1 all over 2. But now I need to switch them. And when I switch them, I don't have f of x anymore. I have f prime. Or not f prime, f inverse. Been doing derivatives too much. I have f inverse of x. Okay? Now, that's how we can find it algebraically. Here we were given a very specific domain. Okay? We were given a very specific domain where x had only 3 values. It had the value -4, 2, and 3. Okay? So let's work through this. F of -4 is f of -4 would be -7. Okay. F of 2, 2 times 2 plus 1 is 5.
7.
F of 3 is 7. Okay, good. So now, if I'm doing the f inverse, the x's I'm going to use are the f of x's. So -7, 5, and 7. If I do the inverse, what do I get? What's f inverse of -7?
-4.
-4. -7 minus 1 is -8, divided by 2 is -4. If I do 5, what do I get? 2.
I'm noticing a pattern.
Yeah. If I do 7, f inverse, keep writing prime. F inverse of 7 is going to be 3. Okay? Now you'll notice here the domain of f became the range of f inverse. Okay? The domain of f equaled the range of f inverse. However, the range of f became the domain of f inverse.
Cool world.
Okay? And this really is, we can see this in our definition of an inverse function right here. If I take a value and I plug it into one function, and I take that answer and plug it into another function, I'm going to get the same thing if I plug that value into the into this f, and then plug that into the other function, g. Both of them should get me back to where I was, okay? So, just to illustrate with a picture here, if I have x, and I do this to get to f of x, and then I take g of f of x, that should take me right back where I started. Okay? So again, this is just a review of things we learned a long time ago with inverse functions.
When?
All right.
In pre-calc?
Probably actually Algebra 2 at some point. But it may have been a while since you saw some of these, so that's why we're doing a quick review. Okay? Now, how do we show that two functions are inverse functions of each other? Well, we're going to use the definition. Alright? So, if I'm trying to prove that f and g are inverse functions of each other, I'm going to take, first of all, f of g of x. Okay? Well, f of g of x is going to be 2 times g of x cubed minus 1. Okay? Well, what's g of x? G of x is this big old cube root of x plus 1 over 2. So that's what I'm cubing, multiplying by 2 and then subtracting 1 from.
We should get x.
Okay? We should get x. So let's see the work. First of all, the cube will undo the cube root. So I have 2 times x plus 1 over 2 minus 1. Well, now the 2's cancel out. And I have x plus 1 minus 1, which equals x. So, the first part works. That's not good enough, though. Because it's possible for one function to give you x when you plug it into the other, but when you reverse them, it's possible not to get back to x. Alright, it's kind of the same idea with derivatives and integrals. You take the derivative and you'll get to the integral. When you take the integral, you don't necessarily get back to exactly the same derivative, the same original function. They weren't exactly inverses. So now we've got to try g of f of x. Okay, so g of f of x. G is the cube root of something plus 1 over 2. So this is going to be f of x plus 1 over 2. So it's the cube root of 2x cubed minus 1 plus 1 over 2. By the way, notice I'm showing a lot more steps than I probably normally would, because I'm trying to show something. I'm trying to prove something. So you don't skip steps. Alright? So this simplifies down to the cube root of 2x cubed over 2, which is the cube root of x cubed, which is also x. So therefore, both of them equal x. Okay? So they are f of x and g of x are inverses of each other. Because we just proved the definition. F of g of x equals g of f of x, and they both equal x. Okay. Now, another thing, just as a reminder, from back when you might have studied this in the past, remember that inverses are reflections across the line y equals x. That's why we saw algebraically up there, to find the inverse, you can switch the x and the y coordinate. Okay? Because to reflect something across the line y equals x, you switch the x and y. Alright? What this test here tells us is whether when we switch the x and y, we end up with a function again. Because a lot of times if you switch the x and the y, it'll end up failing the vertical line test. Okay? And that actually brings us to this idea here. does an inverse function exist? Well, a function has an inverse function if and only if it is 1 to 1. Okay? So way back when you learned about functions and inverses, we had this term 1 to 1. And what 1 to 1 means is it takes the function kind of one step further. Okay? A function, we had a domain and a range, and every number over here got mapped to exactly one value over here. Okay? But one thing that was possible to happen is you could have had a number that was mapped to something over here that already had something else mapped to it. So this right here would be a function, but right here there are two different x values mapped to the same y value. So this is not 1 to 1. Okay? This is a function. A function has each x mapped to one y. Okay? That's what the function was. A 1-to-1 function will have every y coming from only one x. Alright? So, if we were to illustrate this again, we have a domain and range here. Every value over here only gets mapped to one value over here. That makes it a function, but they also get mapped to unique values of the function. Okay? So every one over here gets mapped to its own value in the range. Every value in the range only is the result of one value in the domain. Okay? And if you think about it, it makes sense because when you switch x and y, as we saw up in the warm-up, okay, your domain and range also switch. So in this first example, if we all of a sudden started going the opposite direction, notice this would get mapped back to two different values, not a function. Okay, there's kind of an inverse relationship, but it wouldn't be an inverse function because this one got mapped back to two different values. Okay? Yes?
Does it mean that x squared won't have an inverse?
It doesn't have an inverse function. Okay? Because, and if you take x squared, and let's just look at it, if I reflect that across the line y equals x, notice now it fails the vertical line test. Okay? Now, if we limit the domain of x squared to, let's say, only the x's greater than or equal to 0, then that would only give us this bit. So when we reflect it, it would only give us that. And that would be an inverse function. So there are things where if you limit the domain to make it 1-to-1, then you can have an inverse function. Okay? So that's a good question there. So 1-to-1, okay, 1-to-1 means that every y comes from a unique x. Alright? And notice here, here's a term that we've mentioned in the past but haven't used necessarily a whole lot. If f is strictly monotonic, in other words, it's all increasing or all decreasing over its entire domain, then it is 1-to-1 and has an inverse function. Okay?
But monotonic is like staying the same and never changing, right?
Yes.
Okay.
It doesn't have to be constant, but it's always increasing or always decreasing.
Oh, like monotonous, like a
Yeah.
voice or whatever.
Yeah.
Okay, I understand.
Okay? Question?
For any function whose degree is larger than 1, I guess, it's not going to have an inverse function.
Well, not necessarily, because notice, for example, x cubed x cubed,
That's the function I thought of as a counterexample, but I'm not sure why it works.
well, it works as opposed to x squared. When you take the square root of a number, it's plus or minus, right? The square root of 4 is plus or minus 2. Square root of 9 is plus or minus 3. When I take the cube root of 8, it's just 2.
If you cube something, it'll never be negative.
Yeah. Okay. If I take the cube root of negative 8, I get negative 2. Just one answer every time. Okay. So cube root, you'll notice there, cube root is also, that's where the 3 goes. Is the reflection. Okay, and it's also a function, okay? And that works, that is an inverse function, because this is strictly monotonic. It's strictly increasing over its whole domain.
So any even function will not have an inverse.
Correct. You would have to limit its domain. That's why, you guys remember studying the arctangent, arcsine, arccosine? Those were the inverse functions for sine, cosine, tangent. When we looked at the inverse sine, the arcsine was for angles from negative pi over 2 to pi over 2. Well, why did they come up with that? Well, think about your sine curve. Sine curve, looking like this, obviously is not 1 to 1. However, if we limit it from negative pi over 2 to pi over 2, we just made a portion of it that is 1 to 1. So we can get an inverse function of that. Okay? And that's how we can handle things that are not 1 to 1 initially. We can limit the domain. Alright, and that's why this says if it's monotonic on its entire domain. So yeah, if we say sine where x is between negative pi over 2 and pi over 2, now we have something that's monotonic over its domain, and we can take the inverse, because that is 1 to 1. Okay? Alright, so let's check these, okay? Which of these functions has an inverse function? How would we, okay, well, what would the graph of this look like?
You can do the derivative and just find that.
It's a regular. The first one is a regular cubic function, so it does. And the second one, I think it does the same thing. Let me check.
Here's how you can tell without even graphing.
Yeah, I think it never changes the slope direction.
The second does.
Right. Or does it? Oh no, I'm wrong, wait. Because the slope is a positive power, right? It's square plus 1. Or no. I messed up with 1.
You're on the right track there. There's a number of ways that we could figure that out. Is that the graph of the first one?
Second one.
The second one? Okay. Let's think about this logically and also using the derivative here. Okay? Logically speaking, or algebraically even, could we solve for x? Well, let's, could we, if we switch the x and the y, could we then get the y by itself? Okay? Or, what Evan was saying is it strictly monotonic? How do we know?
If the derivative can ever be negative, then it's or well, in this case, like, okay, if the derivative can either only be positive or only be negative, then it's monotonic.
Okay,
Sorry, I worded that.
that's okay. And really, just to kind of put it another way here, does f prime of x ever, because it could equal 0, right? It could equal 0. But does f prime of x ever change signs? Now, it couldn't equal 0 at more than one point, right?
Mm-hmm.
Does it ever change signs? Or have multiple zeros? Okay, well, let's figure this out. What's f prime? X squared plus 1. Okay? Will that ever equal 0? No.
Oh, is it x squared? It's 3x squared.
3x squared plus 1. Sorry. Will that ever equal 0? No. Okay? Does not ever equal 0. Therefore, is this monotonic?
Yes.
Yes. We could plug something in and figure out if it's increasing or decreasing, but this one's increasing. Okay? Alright, so f prime of x is greater than 0 for all real numbers. Okay? So, does it have an inverse?
Yes.
Yeah. That means it's monotonic, which means it's 1 to 1. Which means it has an inverse.
So once we prove it is monotonic, do we still need to prove like f(g(x) equals to g of x?
No. That, because we don't know what g is. If we were given another function and asked to prove whether the two functions were inverses, then we would do f of g of x and g of f of x. Okay, here we're just saying, does an inverse function exist for this?
Yeah.
But I mean, is it possible to make it like not a function, but some relationship in which which is gonna be inverse to that function?
There will be some. We could find it if we wanted to, but
I'm just not sure.
all this is asking is, does it have one?
Yeah.
Okay. Over here, though, f prime of x is 3x squared minus 1. Well, that's going to equal 0 when x is plus or minus the square root of 1/3. It has multiple zeros, so I know multiple zeros means it's got to have a turning point somewhere, right? So I know this is not going to be monotonic, okay? So there are multiple zeros, at least one turning point. That's actually Rolle's theorem. On an interval where the value equals 0,
But
at two different ends, I know it's gotta change direction somewhere there.
does plateau point apply to first derivative? Plateau.
You can have plateau points, alright?
Yeah.
I know I'm gonna have multiple points though where this is changing, where the derivative equals 0. And we could test it out here. Okay? Negative square root of 1/3 and positive square root of 1/3. If I plug a 0 into my derivative, I get -1, right? If I plug a 1 in, 1 is bigger than the square root of 1/3. So if I plug a 1 in, I'm going to get 3 minus 1, which is positive. If I plug a -1 in, I'm still going to get 3 minus 1, which is positive. Oh, this should be 0, not x, sorry. Okay, so I have more than one turning point. Actually, I have 2 turning points.
But I mean, in some cases, they may have like 2 plateau points. Do you think that's a possibility?
It's possible. Another thing that we could say here is because we know this is a cubic function, the only time you really get plateau points with these is when you had like a multiplicity, when you solved the derivative. If it were like square root of 1/3 with a multiplicity of 2, that's going to end up being like it's a double root. So you can use, now if it's a function you don't necessarily recognize what it looks like, then you might have to do the sign diagram or whatever. But as long as I know there's at least one turning point, that means it's not 1-to-1. And that means there is no inverse function. Okay? So, just some guidelines here, okay? If you are asked to actually find the inverse, first of all, see if it actually has one. Okay? Make sure it actually has an inverse before you start doing all the work. Then, solve for x as a function of y. Then swap the x and y. Now you could do these in kind of reverse order, alright, if you want. If you want to swap the x and y first, then solve for y, that's okay. Either way, you're doing the same thing. Okay? The resulting equation then will be the inverse. Okay? When you define the inverse, you need to also define the domain and range. Okay? So the domain of f inverse is the range of f. Okay? And then you can verify that it works. You can always check your work for this. Okay? So for example, if I'm going to do the inverse function of f of x equals 2x minus 3. Well, first of all, I know that a radical function is going to start somewhere and go like this. Alright, so I know it's monotonic. Okay? As long as there's something linear inside here, I know there's nothing kind of weird going on. Okay, so that's just my knowledge of the parent function and transformations. I know it's going to be monotonic. Alright, so I know there's going to be an inverse. So now, just following the directions here, we're going to solve for x as a function of y. So I'm going to first of all square both sides. I'll make that y squared equals 2x minus 3. I add 3, y squared plus 3 is 2x. And now I divide by 2, and I get y squared plus 3 over 2 equals x. Okay? Now, I can switch our x and y And that tells me that the inverse function of x is x squared plus 3 over 2. Okay? Switch x and y.
It's still in.
Y is now f inverse. Mm-hmm.
It's inverse of derivative.
Inverse. I'm going to do that every time, I think. F inverse. So used to doing derivatives. Okay? It'll get real fun once we start doing derivatives of inverse functions. Okay? Now, real quickly though here, we need to define our domain. What is the range of this radical function? What's our range? Come on guys, this is going back a ways. No, the range is not all real numbers.
I looked at the last function, I'm sorry.
What's the range?
The range is equal to 1.5 or
That would be the domain.
oh, the range. Oh.
The domain is
The range is 0 or more. It's a positive number or 0. 0 to infinity.
okay, yeah, from 0 to infinity, all right? Because the radical function, this hasn't been moved up or down at all, so it starts at 0 and it goes up. All right, so for my inverse function, what's the domain going to be?
Oh, the domain?
Yes.
Infinity.
Huh?
The domain is the infinity.
No, it's not. Not if it's an inverse function.
Oh yeah, I forgot about it. Yeah. Oh.
What's the domain of our inverse? Huh? From 0 to infinity, okay? Guys, look at number 4 right here.
Forgot about
Define the domain of the inverse to be the range of f.
that. Yeah.
So the range was from 0 to infinity. So here, x is going to go from 0 to infinity. Okay? And by the way, we know that the range of this inverse function would also be from 1.5 to infinity. So f inverse of x is greater than or equal to 1.5. Okay? Now, we can also verify, here that f of f inverse equals x and f inverse of f equals x. So let's just do that real quickly here. Okay, so f of f inverse of x. F says to do the square root of 2 times something minus 3. Well, here the something is x squared plus 3 over 2. Okay? So the 2's cancel out. We have the square root of x squared plus 3 minus 3, which is the square root of x squared, which equals x. Okay, so that works. F inverse of f of x is something squared plus 3 over 2. What's the something? It's the square root of 2x minus 3. Okay? So, that's 2x minus 3 plus 3 over 2, which is 2x over 2, which equals x. So, it works. They both turn out to be x. Okay?
Where did you get the range of this function, of the inverse function?
From the domain of the original function.
Yeah, but why is domain from 1 over 2?
1.5. Because if it were anything less than 1.5, then the inside of the radical would be negative.
Oh, it's 3/2.
Yeah, 3/2.
Oh, it's just a different way of writing it. Got you.
Okay? Alright, now, I kind of spoiled 4 a little bit for us, because we already mentioned this when we were talking about 1-to-1. Forgot this was one of our examples. Okay? Show the sine function is not 1-to-1. We saw that because it's periodic. Okay? Show that negative pi over 2 to pi over 2 is the largest interval centered at the origin where it's strictly monotonic. Okay?
May I try to guess the proof, the beginning of it at least?
Okay? What?
May I try to guess the proof, the beginning of the proof?
Okay.
So first we find the derivative of sine, which is cosine, and then we know that cosine has multiple zeros, which makes it impossible to find an inverse function. And that's basically it.
Okay, well let's keep going with that. Here, alright, cosine equals 0 where?
At 0 and pi and 2 pi. And
Not at 0. Cosine of 0 is 1.
oh no, not 0. Then it's pi over 2 and 3 pi over 2. 3 pi over 2, right? That was sine.
Okay, and then we can keep going with these things. So, if we went to negative pi over 2, it's also 0. Okay, so notice, if I were doing a sine diagram, I could just count by pi over 2's. Pi over 2, 0, or I'm sorry, pi over 2.
It has an infinite number of zeros, right?
Yeah. 5 pi over 2. We could go the other way to a negative 3 pi over 2. Okay. If we checked values, for example, cosine of 0 is a positive 1. Cosine of pi is negative 1. Cosine of 2 pi is a positive 1. Alright? Cosine of negative pi is also negative 1. So you'll notice here, these intervals are all a total of of 2 pi, or I'm sorry, of pi units apart. Okay? So I know that that's the longest distance where it will be monotonic. Okay? Now, it also says centered at the origin. Okay? Well, the only thing centered at the origin, here's 0. If I go out to here and out to here, that's the only interval centered at the origin that is monotonic. Okay? It's increasing from negative pi over 2 to pi over 2. If I go any further than those, then it starts to decrease. I have a change in direction, and now we have something that's not 1-to-1 anymore. Okay? So